Hi everyone, welcome back to my YouTube channel. Today's video is about Raster-scan systems and it comes under the subject computer graphics and image processing. In this video, we are going to see about the introduction, video controller, basic refresh operations, enhancing refresh rate and efficiency, advanced operations of video controllers, Raster-scan display processor, additional functions and memory optimization. First, the introduction. Interactive raster graphics system typically utilize multiple processing units. Besides controlling processing unit, that is CPU, a specialized processor known as the video controller or display controller manages the display device's operations. As depicted in figure 1, the frame buffer which stores the image data can reside anywhere within the system memory. The video controller accesses this frame buffer to refresh the screen. Advanced raster systems also incorporate additional processors such as coprocessors and accelerators to perform various graphics operations more efficiently. In the figure 1, we see about the architecture of simple raster graphics systems. Now, the video controller. Figure 2 illustrates a typical organization for raster systems. In this setup, a designated section of system memory is allocated for the frame buffer and the video controller has direct access to this frame buffer memory. Frame buffer locations and their corresponding screen positions are referenced using Cartesian coordinates. Within an application program, graphics software commands are used to set coordinate positions for displayed objects relative to the Cartesian reference frame's origin. However, the origin can be set at any convenient location based on the requirements of a specific application. So we can see that in the figure 2, we have architecture of raster system with a fixed portion of the system memory reserved for the frame buffer. Now, figure 3 is a 2D Cartesian reference frame with origin located at the lower left corner of the screen. In this configuration, the screen surface represents the first quadrant of 2D system. Positive x values increase from left to right and positive y values increase from bottom to top. Pixel positions are assigned integer x values ranging from 0 to x max and integer y values ranging from 0 to y max. However, some hardware processors such as screen refreshing and certain software systems reference pixel positions from the top left corner of the screen. Basic refresh operations of the video controller. Figure 4 outlines the basic refresh operations performed by the video controller. Two registers, that is X and Y, store the coordinate values for the screen pixels. Initially, X register is set to 0 and Y register is set to the value corresponding to the top scan line. The frame buffer's contents at this pixel position are retrieved to set the CRT beam's intensity. The X register is then incremented by 1 and this process is repeated for each pixel along the top scan line. Once the last pixel on the top scan line is processed, the X register resets to 0 and the Y register is updated to the next scan line down. This process continues for each successive scan line. After processing all pixels along the bottom scan line, the video controller resets the registers to the first pixel position on the top scan line and refresh cycle starts anew. So figure 4 is shown here, which says that the basic video controller refresh operations. First we have raster scan generator and then two registers X and Y, then memory address, and from the memory address it goes to the frame buffer, and from the frame buffer it goes to the pixel register and checks the intensity. Enhancing refresh rate and efficiency. To maintain a refresh rate of at least 60 frames per second, video controllers may need to retrieve multiple pixel values from the refresh buffer simultaneously, especially if typical RAM cycle times are too slow. These pixel values are stored in separate register and used to control the CRT beam intensity for adjacent pixel in groups. This method speeds up pixel processing significantly. Now, advanced operations of video controller. First is memory management. Video controllers can retrieve pixel values from different memory areas during different refresh cycles. Multiple frame buffers may be used, allowing one buffer to handle refreshing while others are being updated. This setup is ideal for real-time animations as it enables different views of moving objects to be loaded into a buffer without interrupting the refresh cycle. Next is pixel transformation. Video controllers can also perform transformations on block of pixels such as enlarging, reducing, and moving screen areas during refresh cycles. Lookup tables often Video controllers include a lookup table which allows a pixel values in the frame buffer to reference the table instead of directly controlling the CRT beam intensity. This approach provides a fast method for changing screen intensity values. The last one is mixing input images. Some systems allow the video controller to mix the frame buffer image with an input image from a television camera or another input device, enhancing the system's functionality for various applications. Now, let us see about Raster-scan display processor. Figure 5 illustrates the organization of a raster system with a separate display processor, also known as graphics controller or display coprocessor. The primary function of the display processor is to offload graphics tasks from the CPU. In addition to system memory, this setup may include a dedicated memory area for the display processor. Here we can see the diagram of Raster-scan display processor. A key task for the display processor is digitizing picture definitions from application programs into pixel values for the frame buffer, a process known as scan conversions. For example, scan converting a straight line segment involves locating the pixel positions nearest to the line path and storing the corresponding color values in the frame buffer. Similar methods apply to other objects. Characters can be defined using rectangular pixel grids as shown in this figure 6, or as outline shapes as shown in this figure 7. The grid size for characters varies ranging from 5 to 7 to 9 cross 12 pixels or more for higher resolution displays. These grids are superimposed onto the frame buffer at specific coordinate positions. For characters defined by outlines, the shapes are scan converted by determining the nearest pixel positions to the outlines. Now let us see some additional functions. Display processors also handle various other tasks such as generating different line styles, that is dashed, dotted, or solid, displaying colored areas, applying transformations to objects in a scene, interfacing with interactive input devices like mouse. Memory optimization. To reduce memory requirements, raster systems can organize the frame buffer using techniques like linked lists and color encoding. One method, run length encoding, stores each scan line as pairs of numbers. The first number indicates a color, the second number specifies how many adjacent pixels on the scan line share that color. This technique is efficient for images with long runs of single color but become less efficient with frequent color changes and short runs. Another method is called cell encoding, which organizes the raster as rectangular areas. Although the size of frame buffers is less of a concern today due to reduced memory costs, encoding methods remain valuable for digital storage and transmission of images. This was all in this video. Thank you for watching. Please do like, share, and subscribe.